Hello guys, now we're going to continue looking at the spectral density problem, but we're going to fixate on something else. So we're still working with a real symmetric matrix and it has n real eigenvalues by the spectral theorem. We define the spectral density as the sum of Dirac delta functions which are centered at each of the eigenvalues. So this is the actual spectral density. However, as we can say for example, n equals 5, this is going to be a very discontinuous function. It's not even a function in the true sense of the word. So in particular, it's going to have peaks wherever there's an eigenvalue. So if the eigenvalues are 1, 2, which is going to be a repeated eigenvalue, 3 and 4, it's just going to have peaks, which means it's hard to work with and it's really difficult to approximate numerically. So today we're going to see how we can regularize or approximate, or also known as blurring, the density of state so that we can use numerical methods, and we're going to find different alternative expressions for the density of states once it has been regularized. So there's two main ways of doing this, and they both use kernels, which we're going to convolute on, and it's just using a different kernel. So perhaps the easiest or the most straightforward way of going about this is using a Gaussian kernel. So we're going to define g sigma of t as 1 over 2 pi sigma squared to the 1/2 power exponential of minus t squared 2 sigma squared. So this is just like a Gaussian distribution which is centered at 0 and has sigma squared variance. And what we're going to do is we're going to integrate the kernel and the density of states. So what this is going to do essentially, it's going to replace the Dirac delta functions with g sigma of t minus lambda a. So this is going to replace sort of the discontinuous and very non-linear, the very sort of jumpy peaks with continuous Gaussian centered at that point. So we can see a bit why this is useful, and number one, it's going to give us a smooth function, an infinitely differentiable function, and we do have a parameter sigma here, which will tell us how close of a fit. So for small sigma, it's going to be very close to the density of states. So we're going to have, so if we take very small sigma, for that example, it's going to have very high peaks and very thin peaks. So it's going to be something like this for the previous example. So this is a rough sketch, but for large sigma, it's going to really blur the density of states. So it's going to look something like this. We're going to have a small peak, maybe a higher peak here. We lose detail, but we do gain smoothness. So the other way of doing this is with what is known as a Lorentzian kernel. So the Lorentzian kernel is a bit different. We're going to call it L, and instead of having sigma, we're going to use eta as the regularizing parameter. So this is going to be 1 over pi, and then it's going to be eta t squared plus sigma squared. So it looks really similar to a Gaussian, but it's more pointy or thinner. But it is useful because it will allow us to express the density, the regularized density of states in a very neat way using the resolvant of a particular matrix, and we're gonna take a look at that in a second. So the statement is that the density of states, which has been regularized by the Lorentzian, so this is going to be 1 over n pi, and then instead of having sigma t minus lambda I, we're going to have L eta t minus lambda I, so we can actually do this where you can remove the pi, just keep the n, L eta t minus lambda I, and the sum still goes from 1 to n. So this is going to be 1n pi and eta t minus lambda I squared plus eta squared. So we can express this as the as 1 minus n pi, the imaginary part of I equals 1 to n, 1 over t minus lambda I plus I eta, and we can see this because, well, I'll just write here, proof, because if we take minus 1 over n pi, imaginary part of this, we can swap the sum with the imaginary part. And this will give us 1 minus 1 n pi sum, and this is going to be 1 over 2i, this thing, minus its complex conjugate, and the complex conjugate is just minus I eta instead of plus I eta. So when we combine everything, we can bring the 2i up front, n pi 2i sum of, and we can just bring the two fractions together, so it's going to be t minus lambda I minus I eta plus t minus lambda I, apologies, this is a minus, this is a plus, minus I eta, and in here we're just going to have t minus lambda I squared minus I eta squared, which gives us n pi 2i, and up on the top we're just going to have minus 2i eta, and on the bottom we're just going to have t minus lambda I squared plus eta squared as the denominator. So finally this is just 1 over n pi sigma eta t minus lambda I plus squared plus eta squared. So this is what we wanted, so we're good. So going back to this expression here, this is actually the same as minus 1 n pi sum of oh, no sum anymore, we do have the imaginary part still. I'll actually just write everything we had before. So this is what we had before, and we can write this as minus 1 n pi, the trace or the imaginary part of the trace of this matrix ti minus a plus I eta to the negative power, so the inverse of that matrix. And this is neat because this is, remember, the regularized density of states at t, so we can essentially express this as a single trace as opposed to the kernel polynomial method where we had to do many